let's explore the enigma of Turing patterns. Man has always had an inherent appreciation for symmetry, but nature is not always symmetrical. For instance, why does a cylindrical organism Hydra loses its symmetry to give rise to tentacles at its extremities? Why are leaves arranged the way they are? And what dictates the development of, say, a spherical embryo into a bilateral organism? These questions intrigued Turing. To explain this, he proposed a reaction diffusion model in which he assumed two diffusing interacting chemicals that as a sole driving force for a process known as morphogenesis. This was even before the year 1953 when Watson-Crick duo gave us the double helix model, which means back then the world did not have any understanding of the genetic basis. He published his work in Philosophical Transactions of Royal Society in the year 1952. So what's morphogenesis? Morpho means form, genesis means to form, that is to produce. After gaining a brief insight into the idea of morphogenesis, Vivek will walk us through the Cartesian and the polar equations for the diffusing chemicals. After this, he'll also talk about the Turing instability criteria. Most importantly, does biology agree with all this math? That's what we look at then. Okay, so here we go with a famous Muris analogy that will help us gain some understanding of this mechanism. Assume a grass field and a lot of grasshoppers. Say there is a fire at one spot. The fire activates. Basically, it heats up the grass next to it and causes the grass to burn. So the fire is autocatalytic. Without delving into the physiological accuracy, let's assume that the fire, because of the heat, causes the grasshopper to sweat, and the sweat causes the grass to dampen. So this inhibits the fire. So let's assume, define two variables: the diffusion coefficient of fire, like the rate at which the fire propagates, as df, and the rate of propagation of grasshopper is the rate at which it moves, as dg. So we have two conditions. If fire propagates faster than the rate at which the grasshopper can move, that is, df is more than dg, what do we get? We get a burned area with, say, crispy fried grasshoppers. But instead, if we assume that the fire propagates slower than the grasshopper, so what happens is the grasshopper moves to a certain place, they sweat profusely, and when the fire reaches that area, it can't burn that area because of the dampened grass. So this restricts the charred area to a limited domain. If the fire pops out at random locations with, say, a differential probability, so what we get is a spatial distribution of charred and uncharred regions hosting sweaty grasshoppers. So this idea illustrates the reaction diffusion model, where we ought to have a long range inhibition and the short range activation. So this is essential criteria that must be fulfilled for Turing patterns to exist.
So coming on to the formulation or modeling of these Turing patterns. So this was actually done by Alan Turing himself using what are called diffusion equations. So before coming on to the equation part, let's go to what a general pattern formation is. So a pattern formation is something we see throughout nature, right? So it is basically initially where you have a homogeneous system of all these morphogens, as we had talked about before, that these patterns are formed by the interaction of all these morphogens. So initially we'll have a homogeneous system of these morphogens, which then evolve into something that is not homogeneous at t equal to infinity maybe, but still is a steady state. So not all Turing patterns have, well, general patterns though. So Turing patterns is in fact a particular class of patterns. And the steady state solutions that are observed under these wavelengths are independent of the volume of space they occupy or the boundary conditions. But there is one boundary condition, that is that if, let's say, our given boundary or the given volume has the boundary B, then the morphogen concentration cannot increase or decrease due to the morphogen going outside of the system, neither it coming from outside to inside. That is, the flux across the boundary has to be zero. Next slide, please. Hello. Yeah. So Alan Turing formulated all these Turing patterns using, as I said, diffusion equations. So these diffusion equations are applied on the concentration, or rather, as we will see ahead, the deviation from the equilibrium concentrations at t equal to 0. So basically, let's say if the equilibrium concentration at t equal to 0 is h and k, then x here, as indicated, is basically h minus the concentration at any time t, and well, the respective will be followed for each of the morphogens. So if let's say the deviations are xi for each of the n morphogens, then the diffusion equations are basically the LHS being the basically contributing the time change for each of the deviations, and the RHS having two terms. The first term indicating the source term. It's basically providing us the information about interaction between all of the morphogens, and the second term being the spatial change of each of the concentrations. So that is being multiplied by di, which is basically accounting for the degree of this diffusion and is called diffusion coefficient. And then we have one more equations as seen on the screen, and this is basically indicating that the flux across the boundary for each of the morphogens is 0. That is, none of the morphogens are getting added to the system across the boundary, neither it is going out of the system. Next slide. Yeah. So coming on to the solving part of this equation, sometimes it is easy to solve, but many times, or rather most of the times, it is not, because it can't be solved analytically in most cases. So for those conditions, we use a computer as such. But for now, to get a general idea of this equation, what we'll see is, or rather the model, what we'll see is we'll take a one-dimensional system. That is, the pattern can form only on one line, let's say x-axis. And to simplify the system, we'll take two morphogens, one being x and one being y, or rather x and y being the deviations from the equilibrium concentrations at t equal to 0. And both of these respectively indicate the local densities of each of the morphogens, that is x being the inhibitor and y being the activator. Now, the equation, the diffusion equation that we had seen before, that would boil down to these two equations for each of the morphogens x and y, as indicated here. But you'll see that I've taken G to be linear in this case, and that is only for our simplicity. And in general, it may not be linear because it can interact in more complex ways, that is the morphogens. But for simplicity, for the solution sake itself, we'll take it to be linear right now. And as you can see, the Laplacian, that is the del square term, boils down to dou square by dou x square here, because well, we are only in one dimension right now. Then basically the boundary conditions boil down to the change in each of the morphogen at the boundaries, or rather the boundary points, is equal to 0. I've taken the line to be of length L, by the way, as you can see in the boundary condition. And also, you might see there is some condition written in the black box. That is basically accounting for the fact that when we are going to go to the solving part of this equation, we're going to take x and y to be complex functions. It's just for our convenience because it becomes easier to solve it using x and y being complex functions. But what really matters at the final solution is basically the real part of each of those. So that is why these boundary conditions can be modified a little by saying that real part of each of these is equal to 0. Now coming on to the A, B, C, D constants in the equation, those are basically indicating positive reaction rates, and those account for how the morphogens themselves interact with each other. Now, coming to the first condition for forming Turing patterns, as we had seen in the Murray's analogy, the diffusion coefficient for the inhibitor has to be greater than diffusion coefficient for the activator. I'm not going to repeat why that is the case because this was covered in the Murray's analogy, but a general idea is that the inhibitor shouldn't totally, or rather the activator shouldn't totally dominate over the inhibitor, neither should the inhibitor just totally eat up all the activator. So that is basically the general idea here. But yeah, that is Murray's analogy. Going to the next slide. Yeah. So now coming to the main solving part of the equation, what we'll do is one of the methods to solve this is basically taking the equations or the system of equations in matrix form. So as you can see on the screen, due to having only two morphogens, we can take the vector v to be equal to x, y, a column vector. A being the 2 by 2 matrix as indicated on the screen, this being the matrix of positive reaction rates, or rather the reaction rates themselves, and then D being the diagonal matrix accounting for the diffusion coefficients. So now all of those system of equations can be taken together to form this one diffusion equation, which can be now solved in the usual method we can. So one such method is first doing a separation of variable on V, which is basically taking V to be equal to some diagonal matrix T, which accounts for the time part of each of the X and Y components, and X and Y morphogens, sorry. And then the spatial matrix, which I'll call, let's say, psi, which indicates the spatial part of the components X and Y, or rather the morphogens X and Y. So the psi would be a vector because V is a vector, and T would be a matrix just for accounting to the fact that V is a vector. And these can be applied to form two equations now. I have not shown all of these on the slide, but when you perform it to find the solutions analytically, you can see that this is how it forms. And then you will get two equations, one being the time dependent equation and one being the space dependent equation, that is X dependent equation. And both of these relate by a constant minus k square, which we'll see in further slides. So this minus k square term is what relates both of these. And then you get a relation for k itself, which we'll also see in the further slides. And finally, you can get the Fourier modes. And can I get to the next slide? Yeah. These Fourier modes are basically then summed together using a Fourier series to get the general solution to the diffusion equation. So now the k, as I said before, can be solved using the boundary conditions. And this k here would be equal to, you can see the term pi s by L in the spacem, that is e to the power I pi s by Lx. So that pi s by L is actually the k square I was talking about. So k is equal to pi s by L. Now, the whole term inside the summation is in fact our Fourier modes, with the thing inside the bracket indicating the Fourier modes we get from time dependent equation, and e to the power I pi s by Lx indicating the space part, or the Fourier modes we get from the space part. And both of them can be multiplied because, well, we applied a separation of variables. Now you might see that we have 5 variables now, or rather 5 coefficients which we have not accounted for, that is AS, BS, CS, DS, and P plus or minus. First of all, coming to P plus or minus, P plus or minus is basically the roots of the equation as indicated on the screen. It's a quadratic equation, of course. And the equation is got when you account for the fact that you get one step during the solution of this equation where you have to take the eigenvalue of a matrix. So for that, we basically take the eigenvalues in the general way. And as it's a 2 by 2 matrix, you get a quadratic equation to solve for the eigenvalues. And the roots are basically the eigenvalues of that matrix. And then AS, CS, BS, DS are basically found using the respective eigenvalue problem that we get. And these equations can be found yourself through analytically solving this equation, at least in one dimension. Next slide. Yeah. So now, as I said, k is equal to s pi by L. Now I have written let k equal to this because I have not indicated k in the slides before. We'll see ahead. But yeah, I would call k to be equal to some kind of wave number because, well, you have a 1 by L and a pi. So I'll call it a wave number to get a general sense of that. So this the roots at k, when you analytically solve that quadratic equation, yes. So when you analytically solve for the quadratic equation, you can get this big expression for the roots. And now coming on to finding more conditions in which Turing pattern can form. So one such condition is that, as I had said during the beginning of my talk, that if you want some kind of pattern at t equal to infinity, rather after a long time, you have to have a condition where you don't get a homogeneous system at t equal to infinity. And as you can see, if you go to the previous slide, can you go to the previous slide once? Yeah. Remember we had a e to the power p plus or p minus times t, right, in the time part of the equation. What happens is, if let's say the roots are complex, because the quadratic equation, right? So let's say if the roots are complex and the real part is, let's say, 0 or negative. what happens is there would, if it's a negative case, it can be easily imagined, because if it's negative, it implies that it would go down exponentially at equal to infinity, and it will go down to zero. That is, there is an exponential decrease, or rather a negative growth, as we would say. So that is why we don't want that thing to happen. That implies that the deviation of x and y at equal to infinity is zero, implies we have a homogeneous system. So for that not to happen, what another condition that we have to apply is the real part of these roots for any k should be greater than zero at some wavelength k. So now we'll have some kind of restriction on what k can grow up to. So as you can see, if you apply that, you can get that the first term. Why? In the roots, we have two terms, right? The one outside of the under root and one inside of the under root. The only term that can be imaginary is the term inside of the under root, or rather the whole under root thing itself. And the only part that can be real is the thing outside of the under root. So that is why, to get a restriction on real part of this equation, we'll take the outside of the under root term. And also there would be one more condition. What is that? Is basically, even if you have an exponential growth, because now we are restricting ourselves to real part of this roots being greater than zero, right? So if you have a restriction on that as well, now comes the part where you have to account for the part that there has to be some kind of change at equal to infinity. So what we'll take is, we'll have some kind of oscillatory mode, or rather some kind of oscillatory behavior. And for that, the argument of the root, that is because it's a complex number now, or accounting for the fact that it is a complex number now, the argument of the root has to be not equal to zero. Because it, if let's say it becomes zero, it implies that we have a complete exponential growth. And well, that is good in a way that we have some change, but we want some kind of oscillatory behavior to account for the fact that we want patterns as such. So what we are basically doing here is to avoid homogeneity at equal to infinity. That implies that we are inducing some kind of instability. And this criteria is in fact called Turing instability. Can we go to the next slide? So to find the Turing instability, or the condition for Turing instability, well, what we'll do is basically, as I said, the real part of the roots have to be greater than zero, right? So we'll find the critical k, or the critical wavelength for which this is true, and afterwards it's not. So we account for that matter, and then we have that the argument of these this critical k should also be not equal to zero, or rather infinity as well. So that the new equilibrium consists of some kind of wavelength that accounts for Turing patterns. So taking both of these into account and putting those into the root equation, the equation for the roots, we find that this critical wavelength k naught is equal to this big expression, and respectively we can find the roots at k naught itself by putting them into the equation for the roots. Can we go to the next slide? Yeah. So now the condition was the k naught is the critical wavelength. That implies that all the wavelengths behind that, that is from 0 to k naught, should be less than that, or at least the value of the root. That's basically because because of the fact of how we formulated the roots themselves. And this is only for the positive root. You can also take the negative roots as well, or rather, I shouldn't say negative roots, rather the p minus. So p plus basically accounts for the fact that p plus of k naught is greater than p plus of 0. But for the negative ones, or rather the p minus ones, we'll have p minus of 0 greater than p minus of k naught. That's basically because of the fact of there is a plus or minus in the whole formulation for p of plus or minus. And basically how k increases and how the value of p decreases or increases for a plus or minus. Basically accounting for that matter, we'll find this, that is p of plus of k naught being greater than p plus of 0. And respectively, if you do for the minus part, you'll get p minus of k naught being less than p minus of 0. So here I've taken the plus part, but you can find the same criteria for the minus part as well. But anyway, putting p plus of 0 into the equation, and then solving this inequality gives us a new inequality. And remember how we started this whole thing. We just said that we want the instability criteria, or the region in which we get Turing patterns. And in fact, solving for this, if a plus d over root bc is a value such that it lies between these two numbers, that is dx plus dy over root dx dy, and also the left hand part, If this value lies between these two values, then we will always get Turing patterns. So I have just plotted this graph here. So basically, the yellow region indicates where we get Turing patterns, that is a plus d by root bc values for the respective dx by dy values. So from the phase diagram, we can account for one fact, that if a plus d by root bc is equal to 2, for any dx by dy, given that dx is greater than dy, of course, that was one of the condition. That is, for any dx by dy, we will always get Turing patterns. So that is one of the observations you can see. Now coming on to a more complex system, that is a 2D system, which is most of the time what we see in the real world, because patterns form on 2D surface and stuff. But yeah, 3D is also possible. But we'll not see the 3D system here, but the analogy can be further taken on for the 3D system as well. Anyway, coming on to the 2D system, uh, the Laplacian now will be having two terms instead of one term. As we had seen in the previous one, that is 1D system, we had dou square by dou x square. Now, let's say we are taking in a Cartesian system, then we'll have the Laplacian being equal to, that is the del square being equal to dou square by dou x square plus dou square by dou y square. And also for simplicity, I've still taken g to be linear, as the source function to be linear. And also the boundary conditions change in a similar way, because we are dealing with 2 dimensions here. So this equation can also be solved in a similar way to the 1D equation. Why? Because now what you will do is you apply separation of variable thrice instead of, twice instead of once, because there we had applied separation of variables or once to get the spatial term and the time term. Now you will apply once to get the time and spatial term again, but now you'll split the spatial term into twice again. That is to get the x term and the x dependent function and the y dependent function. So these can be solved in a similar way to get the Fourier modes, and you'll get the similar Turing instability criterion as well. But anyway, coming on, you'll in fact get the same instability criterion, by the way. You can solve for it and check. So anyway, coming on to the patterns that we see through this formulation are these. So as you can see, the geometry of space itself matters to the solution or the Fourier modes itself as well. As you can see, how these pattern form is basically, let's take the first case, n equal to 1 and m equal to 0. By the way, n and m are basically parameters that we get after solving it. Example, in the 1D case, we had s as a parameter because we had one spatial term. Now we have two spatial terms, implies we have two parameters, n and m. And let's say n accounts for the x term and the m accounts for the y-axis term. X and y are spatial terms, by the way. I'm not talking about the x morphogen and y morphogen. So anyway, coming on to that. So now talking about the morphogens in each of those rectangles. So let's take the black rectangle, or rather the gray rectangle. In that, what's happening is basically the activator concentration, that is the y morphogen, is dominating over the x morphogen. And accounting for the fact that we are dealing with Fourier modes, and as we had seen, these Fourier modes follow some kind of sinusoidal function. So that is why the sinusoidal maxima would be for y at the gray square or the gray rectangle, and the sinusoidal minima would be for x, accounting for the fact that it has to be colored. For the next part, we have the white square or the white rectangle, and what happens there is basically the opposite of what's happening in the gray square or gray rectangle. Why? Because now we have a sinusoidal maxima of x there, and we have sinusoidal minima of y in the same rectangle. So what happens is you have the colored rectangle, so the activator dominates, and you have a discolored rectangle where the inhibitor activates, or rather inhibitor dominates. And also all of these have been drawn at t equal to 0 for simplicity, but the time evolution can be seen if you put on to the fact that you are basically taking the real part of the whole equation. Next slide. Yeah. Now coming on to a less simple geometry, it's basically because in real world, most of the time we don't really take x y coordinate systems always, or rather the Cartesian system always. So we have to account for, let's say, flower or something. So it's better to take better to take systems like polar system, or maybe sometimes hyperbolic system and stuff. So for those, the equations become less simple, and sometimes it's not even analytically possible to solve. But yeah, we still have one equation that will be there if you want to, well, put it on a computer to so basically see the evolution of the pattern or something. So the solutions become more complicated because what we are essentially solving is the Helmholtz equation as shown in the screen. It's basically the Laplacian of psi, the spatial part of V, equal to minus k square, the spatial part itself. So as I remember, as I said, we'll see the k square term. So this minus k square is what relates the spatial equation to the time dependent equation. So you can also see how the time dependent equation looks like. You can solve for that at your own convenience. And also next is that the boundary condition is preserved for a psi. Why? Because the boundary condition does not depend on the time itself. So that is why we can take out the time part and just apply the boundary condition to the spatial part. And that is why the restriction for k values are given by this boundary condition. Can we go to the next slide? So now coming on to the solving of this general equation, it's complex, yes, or maybe most of the times complex. But sometimes, let's say if a system has some kind of symmetry, so let's say a square symmetry or hexagonal symmetry or a rhombic symmetry, what happens is the symmetry is preserved or is seen to be preserved in the equations themselves, and that is basically due to the property of the Helmholtz equation. That's another thing. But if you account for that matter, what you see is, example, if you take the A figure given here, that's basically the hexagonal, basically the system is hexagonal. So the symmetry, as you can see, is preserved in the patterns themselves. And as you can see, K ranges from pi, 2 pi, or so on, 3 pi, n pi. So when you take successive patterns, you can see that the hexagonal symmetry is preserved in each of those patterns. Similarly, you can take the B figure, which is basically for a square system. The square symmetry is preserved there as well, and that can be set for the rhombic system as well, as given in the C part. Next slide. So coming to something that we use many times, or rather most of the times, to, let's say, see the Turing patterns in different systems. One of such systems or one of such problems where we use a kind of coordinates is basically the polar coordinates, or rather the polar system. So why this is useful is because it has both radial and, or it accounts for both radial and angular symmetry. And that is useful because when we take example, the Fourier modes here, as you can see, by the way, the solving part of this is again in a similar way to all of this equation we had seen for 2D system. The one thing you have to care about, or rather a new thing to see about, is basically the angular part, because the radial part is just a one-dimensional system. The angular part is different because now a system you can take is a ring. So what happens on a ring is basically the boundary condition boils down to V. Remember V, we had V to be equated to the column vector xy. So now the boundary condition becomes V of 2 pi plus theta is equal to V of theta. And when you solve, or when you account for that boundary condition and put it into the Helmholtz equation for the spatial part, what we see is k can range from values 1 to any natural number till infinity. And that's what we find. And that is useful because you can see example in the second figure. If we take the ring, the outside ring itself, we actually are solving for this equation. That is, if we take the system to be a ring, and then to get a general solution of, for, let's say, accounting for the radial part also, what we see is we can take this ring and then, well, collapse it to the origin itself and basically extend it to the origin rather. So if we extend it to the origin, we get this cyclic kind of figure as shown for n equal to 0, m equal to 2, where n is basically the parameter for the radial part and m is the parameter for the angular part. Similarly, if we account for the radial part now, we get one-dimensional equation, a sinusoid, and then this is basically all at t equal to 0, by the way. So then we can just rotate it using the angular, because the angular part is independent here. So basically rotate it to get this radial figure as we can see for n equal to 1 and m equal to 0. Any of those parameters being equal to 0 implies the figure is independent of that respective component. So now Combining both of these gives you a general solution, or rather a special solution for n equal to 1 and m equal to 2. It's basically a combination of both of them. For the matter that one you have, because you have applied separation of variables. So basically the solution for n equal to 1, m equal to 2 will be basically multiplying the first one with the second one to get the third one. So n equal to 1, m equal to 2. And you can see that both of those symmetries have now been combined. This is useful because in nature, in many cases, we find radial, angular, or angular symmetry, or in fact, a combination of them. So one of such cases will be shown afterwards in zebrafishes. So that would conclude my part of the whole slideshow. Yeah, thank you.
Yeah. So we looked at the analytical solutions and computational simulations, but for researchers to agree on reaction diffusion as the mechanism for biological patterns, we need to have strong experimental evidence. This comes from a series of experiments done on zebrafish. Zebrafish are interesting striped model organisms whose molecular and genetic bases have been thoroughly investigated. So, Yagamuchi and her team in 2006 uh, used zebrafishes to investigate the dynamism of these patterns. Studies have shown that in the fins and the skin contain three types of pigment cells, that is the melanophores, the xanthophores, and the iridophores. The iridophores are seen to have a slightly not so important, that is a supplementary role in the pattern formation, because the mutant species in which the iridophore was absent also showed similar patterns. So iridophores are have a supplementary role which reduces the system of three chemicals to a two chemical model, which interestingly maps into the curing mechanism. So in the experiment, we see that the researchers have ablated a section of the stripes and observed the regeneration of the stripes. So they observed that after a week of photoablation, the melanophores in the ventral part of this region where the stripe was removed became thicker, as we see in this presentation video. So after a week, the melanophore started buckling upwards towards the region where the strips was absent. So this shows how, despite artificially removing the strips, the molecules rearrange themselves so that the initial distancing between the strips is maintained. So this can be curiously, we can see that it can be simulated well, and it strongly agrees with the results from the reaction diffusion model. So how does this happen? Studies have also shown that melanophores and xanthophores inhibit each other. That is, in vicinity, they are responsible for the death of the cells, but at a distance, they are responsible for each other's survival. This kind of curious mechanism interestingly maps on the activator and diffuser structure of the reaction diffusion. Though the process does not happen exactly like a diffusion model, the cells interact through protrusion, but the length of the protrusion mimics the short range and long condition of the reaction diffusion model. So, math, good enough. It helps us, but biology being what it is, it's complex, and so it's the math, although correctly predicts the mechanisms, but the actual working of the might be slightly different. So thank you. And on a curious note,
I was
I used, yeah, hello,
yeah, Yashvita, can you go to the previous slide once?
this one.
No, I was saying previous slide. Yeah. So
Yeah.
in this one, basically an app, as Yashvita said before, this is basically modeled using diffusion equation. But how exactly is basically, if you take at, let's say, some instant, what you do is you have the general solution already, right? So you do a Fourier analysis to get each of those coefficients themselves, and then use that, and then see the time evolution part of that to get the respective rest of the figures. So let's say if we take the 13-day mark, we use Fourier analysis to get the coefficients, to get the pattern at that point of time, and then let the time evolution part do its magic on that to get the rest of the patterns. How we model the real life patterns themselves. Yeah, that would conclude my part. Thank you, Yashvita.
Yeah, and it's indeed curious to see how the experimental results match so well with the computer simulation.
Thank you so much, Vivek and Yashita, for that wonderful talk. We thoroughly enjoyed it. It was a brand new aspect of science we haven't seen before, at least the most of us. Thank you very much.